In this video here, we're going to take a look at the order of an algorithm. Now, the order of an algorithm, which can also be called the complexity of the algorithm, tells you how changes in the size of a problem affect the approximate time taken for its completion. Now, this is sometimes called the runtime of the algorithm. So just so you're aware here then, you might sometimes see it referred to as the runtime of the algorithm. They just mean the same thing. Now, the order of an algorithm can be described as a function of its size. So if an algorithm has order f of n, then increasing the size of the problem from n to m will increase the runtime of the algorithm by a factor of approximately f of m over f of n. And the number of steps required to complete an algorithm is often used to determine its order. So to begin with here, let's just derive the order of a bubble sort. So let's just take a quick look then at how we can derive the order of a bubble sort. Now, as we mentioned before, the number of steps needed to complete an algorithm is often used to determine its order. And for a bubble sort, most of these steps are related to making comparisons between pairs of numbers. So, if a list has n items, the first pass will require n-1 comparisons. If we then assume some swaps are made, a second pass will be required, and this will require a further n-2 comparisons. And if this process is to continue such that n-3 comparisons are required for the third pass, and n-4 comparisons for the fourth pass, and so on, you get the idea, this carries on up to a single comparison in the final pass. And therefore, the total number of comparisons would then be the sum of these comparisons, right? 1 plus 2 plus 3 plus so on and so on, plus n-3 plus n-2 plus n-1. If we evaluate this here then, so this is the sum of the first n-1 terms, we get a half n-1 times n, which is equal to a half n squared minus a half n. And as we can see then, this here is a quadratic expression. And therefore then we say that the bubble sort has quadratic order. So that's how we derive the order of a bubble sort. Now, that's what we call quadratic order, but there's a few different types of orders that you do need to be familiar with. So let's just take a quick look at those before we work through some practice questions together. So as we just mentioned, then there are some common orders that we do need to recognize here. The first one is linear order, which we just denote as n. For the next one here, this is quadratic order, which we denote as n squared. We've already seen an example of this, right, when we derive the order of a bubble sort. And then finally here, we have cubic order, which we denote as n cubed. Now we can also use the following simplified rules for linear, quadratic, and cubic order algorithms. And please do commit to learning these rules here. These won't be given to you in your formula book, and they won't be given to you as part of the question here. So please do learn these simplified rules for linear, quadratic, and cubic order algorithms. So, if the size of a problem is increased by some factor k, then an algorithm of linear order will take approximately k times as long to complete. An algorithm of quadratic order will take approximately k squared times as long to complete. And then finally here, and you might have guessed this as well, an algorithm of cubic order will take approximately k cubed times as long to complete. So to finish with here then, let's just work through some examples together and see what can be asked of us for the order of an algorithm. So let's just get started then with question 1 here. Now for question 1 then, what we've got here is an algorithm for multiplying two n by n matrices together. And this can be shown to have cubic order. We're then told that the algorithm is applied to programming software to multiply two 400 by 400 matrices together, and it completes this operation in 0.18 seconds. So all we want to do here then is just estimate the time needed by the programming software to apply the algorithm to multiply two, and then for part A here, 800 by 800 matrices together. So for part A then, where do we begin here? Well, the first thing that we need to find here is the factor, right? In other words, what does the size of the problem increase by? So, just notice here then, working with square matrices, right? N by n matrices. So, to start off with then, n is equal to 400. And then for part A here, n is equal to 800. So I'm hoping the factor is quite obvious. So the factor here is simply 2. If you weren't too sure how to kind of evaluate the factor then, what you'd simply do here is take this value of n, 800, divided by this value of n here, 400. And that would give us k is equal to 2 there. Okay, hopefully nice and easy just to get us started there. So now to estimate the time needed by the programming software here to apply the algorithm to multiply two of these matrices together here, these 800 by 800 matrices together, then in that case here, it would be this time, so that's 0.18 seconds, to get 0.18, and what we now do here is times that by k cubed, because the algorithm here has cubic order. So that tells us then that we cube our factor. So k cubed there, okay? So we get 0.18 times by 2 cubed. Like so. So you need to do at this point here is just put this into your calculator, right? So I'll quickly grab my calculator here. 0.18 times by 2 cubed, which is 8. Input that, and what we get here is 1.44. We get 1.44 there. So in other words, let me just make a note here. It would take approximately so it would take approximately 1.44 seconds to multiply 800 by 800 matrices. Okay, so there we have it then. Hopefully nice and easy there just to get us started. That gives us the solution to part A. Now for part B then, again, it's pretty much identical, right? The thing that changes here then for part B is n now is equal to 1,000. But again, the method and the working here is almost identical. All we now need to do here is just evaluate the new k. So k in this example here for part B, it would be 1,000 divided by 400, which is just the same then as 2.5, right? So k here is 2.5. And again, all we do here is take this time, so that's 0.18, and we times it by k cubed here. So k is 2.5, so 0.18 times by 2.5 cubed. Again, just input this here into your calculator. And if you do this correctly then, what do we get here? So 0.18 times by 2.5 cubed. And what that gives me here then is 2.8125 there. I get 2.8125. And therefore then, if we just make a note here, it would take approximately, so let's just run this here to 2 decimal places, right? That would be approximately 2.81 seconds. 2.81 seconds to multiply 1,000 by 1,000 matrices. Okay. And there we have it then. So again, hopefully nice and straightforward there. That gives us the solution to question 1. And then finally, to finish with here, we now have the very last question, question 2. So for this question here, what we're told then is the first fit decreasing algorithm has quadratic order. It takes a computer application 0.15 seconds to apply the first fit decreasing algorithm to 100 items. So for the first part of this question, part A, all we want to do here is just briefly explain what is meant by a quadratic order algorithm. So for part A then, let's just do this underneath here. What do we need to say here then? So basically, we just want to explain then what would happen if the size of the problem is multiplied by k under a quadratic order algorithm. So let's just make a note here then. So if the size of the problem is multiplied by k multiplied by k, then under a quadratic order algorithm, the algorithm will take approximately k squared times as long to run, right? That is under a quadratic order algorithm with quadratic order. If we had cubic order, it would take approximately k cubed times as long to run. And if we had a linear order algorithm, then it would take approximately k times as long to run, right? So, because it's quadratic order here, the algorithm will take approximately k squared times as long to run. As long to run there. Okay. And there we have it then. So that's all we need there for part A. Hopefully nice and straightforward there just to get us started. And then finally, for the very last part of this question here, part B, it just says estimate how long it would take the computer application to apply the algorithm to 800 items. So this here is 0.15 seconds is for 100 items. So in this case here, we've now increased the algorithm to 800 items, right? So what is the factor here? In other words, what is k? So it would just simply be 800 divided by 100. So 800 divided by 100, nice and straightforward then, is simply 8. Okay, so my factor here, k, is 8. So therefore k equals 8. And in that case then, the estimated runtime here to apply this algorithm would simply be this time. It's going to be 0.15 times by 8 squared because we have quadratic order here. So 0.15 times by 8 squared. Again, just grab your calculator here. So 0.15 times by 64. What this gives us here is 9.6. Okay, so we get 9.6 there. Don't forget here the units of time, right? This is 9.6 seconds. Okay, and there we have it then. We don't need anything else other than that. That's absolutely fine. And there we have it then. So it gives the solution here to the very last question, question 2. And that brings us to the end then of this video here on the order of an algorithm.